Tonight, we're going to talk about something 238,000 miles above your head, something you have looked at your entire life, something your parents looked at, and their parents before them, and every generation of human beings stretching back further than memory can reach. The moon. It has been there every night of your existence, following the same slow arc across the sky, showing the same face, wearing the same craters it has worn since long before anything alive existed on this planet to look up and notice. For most of human history, the moon was the definition of unchanging. Philosophers used it as a symbol of constancy. Poets wrote about it as the one thing in the sky you could count on. And even after the space age began, even after 12 astronauts walked on its surface and brought back 842 pounds of rock, the scientific consensus was essentially the same as the poetic one. The moon was finished, geologically complete, a world that had done everything it was going to do billions of years ago, and was now simply sitting there, cooling quietly in the vacuum, waiting out the rest of time. That understanding held for decades. It was comfortable, and it was wrong. Over the last 20 years, every major space agency on Earth has pointed increasingly sophisticated instruments at the moon, orbiters with cameras sharp enough to resolve individual boulders, spectrometers that can identify the chemical signature of a single molecule on a sunlit slope, radar systems that can peer through the surface into the rock beneath, seismometers so sensitive they can detect the footfall of an astronaut. And what those instruments have found, quietly and persistently, has overturned almost everything we thought we knew about the world next door. The moon is shrinking. Its circumference has decreased by roughly 150 feet over the last several 100 million years, and the process is not finished. It is ongoing right now, generating cracks and faults across the entire surface that scientists have only recently begun to map. The moon is shaking. Instruments left behind by the Apollo astronauts recorded thousands of seismic events during the 8 years they operated, including quakes strong enough to register magnitude 5. And when those quakes struck, something happened that nobody expected. The vibrations did not stop. They kept going for minutes, then for hours, reverberating through the lunar interior in a way that made one scientist describe it as the moon ringing like a bell. The moon contains water, not pools or streams, but ice, locked in the permanent shadows of polar craters and possibly scattered more widely across high-latitude slopes, where the sun never reaches at the right angle to melt it. Multiple missions from multiple nations have confirmed it. The question is no longer whether the water exists, but how much there is and whether we can extract it. The moon once had a magnetic field, not a weak one, a field that may have been stronger than the one protecting Earth right now. It was generated by a churning liquid core, the same mechanism that powers Earth's magnetic shield. At some point that core solidified, the churning stopped, and the field collapsed. The moon has been exposed, unshielded, to the full force of the solar wind ever since. And the moon is leaving. It is drifting away from Earth at a rate of 3.8 centimeters per year, measured with extraordinary precision by bouncing laser beams off the mirrors that Apollo astronauts placed on the surface more than 50 years ago. The distance is growing. The days on Earth are getting longer, and this process has been going on for billions of years, which means the moon you see tonight is not in the same place it was when life first appeared on this planet. It is not even close. Each of these facts on its own would be remarkable. Taken together, they describe a world that is not dead at all. It is still active, still evolving, still responding to forces that reach from its cooling interior all the way out to the gravitational pull of the planet it orbits. And the deeper scientists look, the stranger the picture becomes, because there is one more thing happening on the moon that has defied explanation. For over 800 years, people have been seeing flashes of light on the lunar surface since at least 1178, when a group of monks in Canterbury, England, reported watching the moon's upper edge split apart with fire and sparks shooting from the division. Since then, thousands of similar events have been documented, brief flashes that last a fraction of a second. longer glows that persist for minutes or hours, temporary colour changes, mist and hazes that appear and disappear over specific craters. They are called transient lunar phenomena, and as recently as October and November of 2025, a Japanese astronomer recorded 2 bright flashes on the moon's surface within 48 hours of each other. Some of these events have clear explanations. Meteorites slam into the moon regularly, and each impact produces a visible flash, but others do not fit that pattern. The longer lasting glows, the colour shifts, the haze is concentrated around certain craters. These suggest something coming from within the moon itself. Gas perhaps, escaping through the same cracks and faults generated by the same contraction that is producing the quakes. The shrinking, the cracking, the shaking, and the flashing may all be connected. Symptoms of a single underlying process that is still, after 4.5 billion years, working its way through the interior of a world we assumed had gone quiet. By the end of tonight, you are going to understand all of it. What is happening inside the moon right now? Why it matters for the astronauts we are planning to send there. What the geological record tells us about where this process might be heading, and what the moon's slow transformation reveals about the forces that shape every rocky world in the solar system, including the one you are lying on right now. Before we get started, if you enjoy this kind of deep exploration, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let us begin. To understand what is happening to the moon right now, we need to start with what happened when we first listened to it. Because in 1969, when Apollo astronauts placed a seismometer on the lunar surface for the very first time, the data that came back was so unusual that the scientists receiving it genuinely wondered whether the instrument had been set up incorrectly. The signals looked like nothing they had ever seen from Earth. They rose slowly, they decayed even more slowly, and they lasted for over an hour. That was from a natural event, a small moonquake or a distant meteorite impact. Nobody was certain which, but the pattern was unmistakable and deeply strange. On Earth, seismic waves from a comparable event would have dissipated in seconds, maybe a minute at most. On the moon, the ground kept vibrating long after the source of the disturbance had gone silent. It was as if the energy had nowhere to go, as if the entire body of the moon was holding on to it, passing it back and forth through its interior like sound echoing in a cathedral. The Apollo 11 seismometer operated for only 3 weeks before it lost power. It was a preliminary instrument, designed more as a proof of concept than a long-term monitoring station. But in those 3 weeks, it recorded enough to convince scientists that the moon's seismic behavior was fundamentally different from anything they had modeled. The next missions would carry better instruments, deploy them with more care, and leave them running for years. And the picture that emerged from those instruments would reshape lunar science entirely. On November 20th, 1969, the Apollo 12 mission executed an experiment that had never been attempted before. After the astronauts had returned safely to the command module in orbit, mission controllers directed the spent ascent stage of the lunar module to crash into the moon's surface. It struck approximately 85 miles from the seismometer that the Apollo 12 crew had deployed earlier during their surface operations. The impact carried the force of roughly 1 ton of TNT. Scientists expected a brief seismic signal, a sharp spike followed by a rapid decay, similar to what you would see from a small explosion on Earth. What they recorded instead was something that would become one of the most quoted results in the history of planetary science. The moon vibrated for more than 50 minutes. The seismic signal did not spike and die. It built slowly, rising in amplitude over the first several minutes, reaching a peak around 7 or 8 minutes after impact, and then decaying with agonizing slowness over the next 3/4 of an hour. The pattern looked nothing like an earthquake. It looked like the response of a solid, rigid body that had been struck and was now resonating, its entire structure carrying the vibration forward long after the source of the energy had been spent. The scientists monitoring the data used a phrase that would follow this discovery through every textbook and documentary for the next half-century. They said the moon rang like a bell. It was a metaphor, not a literal description. Nobody heard anything. Sound cannot travel through vacuum, and the vibrations were far below the frequency of audible sound in any case. But the analogy captured something real and deeply important about the moon's interior. Something was allowing seismic energy to travel extraordinary distances and persist for extraordinary durations without being absorbed. On Earth, water in the rock, the liquid outer core of the atmosphere, and the plasticity of the mantle all work together to absorb and scatter seismic energy. The moon appeared to lack all of those dampening mechanisms. It was dry, it was rigid, and it was cold enough, at least in its outer layers, to transmit vibrations the way a block of granite transmits the tap of a hammer. NASA repeated the experiment. They did not do it once. They did it on every subsequent mission that had hardware available to sacrifice. The Saturn V third stage from the Apollo 13 mission was directed into the moon, striking with the force of 11.5 tons of TNT. The seismic signal it produced was 30 times stronger than the Apollo 12 impact and lasted even longer. Apollo 14 and Apollo 15 contributed their own spent hardware to the program. Each impact confirmed the same strange reality. The moon holds onto seismic energy the way Earth does not. Vibrations from some of these artificial impacts persisted for more than 3 hours. Between 1969 and 1977, the Apollo Seismic Network recorded more than 13,000 individual seismic events. Some were meteorite impacts, some were the artificial crashes, but the majority were natural moonquakes generated by the moon itself. And as the data accumulated, scientists began to sort these quakes into categories that revealed something surprising about the interior of a world everyone assumed was inert. There were 4 types. The first and most common were deep moonquakes, originating roughly 700 to 1,100 kilometers below the surface. These were caused by tidal forces, the gravitational flexing of the moon's interior as it orbited Earth. They were regular, predictable, and generally mild, more of a slow creaking than a sudden break. The second type were thermal moonquakes, caused by the extreme temperature changes on the lunar surface. Every 2 weeks, the boundary between the sunlit side and the dark side sweeps across the landscape. The surface temperature can swing from roughly 250 degrees Fahrenheit in direct sunlight to minus 280 degrees Fahrenheit in shadow. That transition applies enormous thermal stress to the upper layers of rock and soil, and the result is a faint but detectable cracking as the surface expands and contracts. The third type were meteorite impacts. The moon has no atmosphere to burn up incoming debris, so rocks of all sizes reach the surface at full speed. Each impact generates a seismic signal that the network could detect and locate. And then there was the fourth type, shallow moonquakes. These were different from the others in almost every way that mattered. They originated near the surface, within the upper 100 miles or so of the crust. They were infrequent. Between 1972 and 1977, only 28 were recorded, but some of them registered up to 5.5 on the Richter scale, which on Earth is energetic enough to crack plaster and move heavy furniture. And because of the moon's rigid dry structure, because of the ringing bell phenomenon, once these shallow quakes started, they did not stop for a very long time. Every single shallow moonquake recorded by the Apollo network lasted more than 10 minutes. Some lasted significantly longer. On Earth, even the most powerful earthquakes stop shaking in less than 2 minutes, because the planet's interior absorbs the energy. Water weakens the stone. The fluid outer core bends and scatters the waves. The atmosphere itself provides a subtle but real dampening effect. Remove all of those and you get the moon, a world where a magnitude 5 event does not shake for 2 minutes and stop. It shakes for 10 minutes, or 20, or more, and the seismic energy reverberates through the interior in patterns so complex that scientists struggled to untangle them with the instruments they had. Clive Neal, an associate professor at the University of Notre Dame, led a team that re-examined the Apollo seismic data decades after it was first collected. His conclusion was blunt. The moon is seismically active, and the shallow moonquakes in particular represent a genuine hazard for any future human presence. The moon's surface is dry, fractured gravel and dust. It has no capacity to absorb or redirect the energy of a quake. When the ground moves, everything sitting on it moves with it, and it keeps moving until the energy finally dissipates through the rigid stone beneath. The most unsettling detail was not the strength of the quakes or even their duration. It was the fact that nobody knew where they were coming from. The Apollo seismometers were all clustered in one relatively small region on the near side of the moon. The network could detect that a shallow quake had occurred, but it could not accurately pinpoint the epicenter. The scientists knew something inside the moon was breaking, violently enough to generate sustained shaking that would threaten structures, but they could not say where the fractures were or what was causing them. Then, in 1977, the seismometers were turned off. Budget decisions, shifting priorities, the end of the Apollo program. The instruments went silent, and for nearly 50 years the moon went unmonitored. During that silence, scientists assumed the picture was essentially complete. The moon was seismically active, yes, but in a manageable, understandable way. Tidal quakes from Earth's gravity, thermal cracking from the sun, the occasional shallow event of uncertain origin. It was a quiet world with a few geological ticks left over from a more active past. That assumption held until a new generation of cameras, flying aboard an orbiter called the Lunar Reconnaissance Orbiter, began sending back images of the surface at a resolution the Apollo-era scientists could not have imagined. And what those images revealed was not a relic of the past. It was evidence of something happening right now. Something that explained the shallow quakes, the sustained vibrations, and the strange signals that had puzzled scientists since 1969. The moon was not just cooling, it was shrinking, and the entire surface was cracking apart because of it. In 2010, a senior scientist at the Smithsonian Institution named Tom Waters published a finding that would change how we think about the moon. Using images from the Lunar Reconnaissance Orbiter camera, the most detailed orbital photography of the lunar surface ever obtained, Waters and his team identified thousands of previously unknown features scattered across the moon's highlands. They were called Labate scarps, and they looked like small stair steps cut into the landscape. Cliff-like ridges, some of them several miles long, where one section of the surface had been pushed up and over the section next to it. These were not ancient features. They were young, in geological terms, startlingly young. The craters around them showed minimal degradation. Some of them appeared to cut across small impact craters, which meant the scarps had formed after the craters, and many of those craters were themselves relatively recent. The conclusion was unavoidable. These features were being created by forces that were active now, not billions of years ago, but in the geologically recent past and likely in the present. The mechanism Waters described was simple in principle and enormous in consequence. The moon's interior is still hot. Not as hot as it was when it formed 4.5 billion years ago, but hot enough that the core and deep mantle retain significant thermal energy. That energy is slowly radiating away into space. As it does, the interior cools, and as the interior cools, it contracts. If the moon were made of something flexible, something that could deform slowly and smoothly as the interior pulled inward, the contraction would be invisible at the surface. But the moon is not flexible. Its crust is brittle rock, a rigid shell wrapped around a slowly shrinking interior. When the interior contracts, the crust does not have the option of gently settling inward. It breaks. It cracks along lines of weakness, and one side of the crack is pushed up and over the other by the compressive force. The result is a thrust fault, and the surface expression of a thrust fault is a Labate scarp, a small cliff where the ground abruptly steps upward. Think of a grape, drying into a raisin. As the interior of the grape loses moisture and shrinks, the skin wrinkles and folds, because there is too much surface area for the reduced volume beneath. The Moon is doing the same thing, except instead of skin, it has a layer of cold, brittle rock, several miles thick, and instead of wrinkles, it produces fault scarps that can be miles long and tens of feet high. The analogy is imperfect in one important way. A grape wrinkles slowly and silently. The Moon's crust does not yield quietly. When the compressive stress exceeds the strength of the rock, the crust breaks suddenly, and the break produces a moonquake. The magnitude of the shrinkage is not large by human standards. Over the last several 100 million years, the Moon's circumference has decreased by approximately 150 feet. That is less than half the length of a football field, distributed around a circumference of nearly 6,800 miles. If you could somehow watch the process in real time, you would not see anything happening, but the instruments can detect it. The faults are there, the scarps are there, and the quakes generated by the faulting are there, recorded in the Apollo data, and now linked directly to the features visible in orbital photographs. Waters made that connection explicit in a study published in January 2024 in the Planetary Science Journal, working with Nicholas Schmer at the University of Maryland, Renee Weber at NASA's Marshall Space Flight Center, and other colleagues. Waters analysed the locations of the lobate scarps in the lunar South Polar region and compared them to the estimated epicenter locations of the strongest shallow moonquakes recorded by the Apollo seismometers. The result was striking. One of the most powerful shallow moonquakes ever detected by the Apollo network had its probable epicenter in the South Polar region, and the area around that epicenter contains young thrust fault scarps. The team demonstrated through modelling that the formation of one specific scarp, located within a candidate landing region for NASA's Artemis 3 mission, could have been associated with a moonquake of the recorded magnitude. To put that in more direct terms, the exact area where NASA plans to land the next humans on the Moon sits near an active fault that has already produced at least one significant earthquake, and that earthquake would have generated sustained shaking lasting far longer than any comparable event on Earth, because of the ringing bell phenomenon that Apollo discovered 55 years ago. The team also modelled what happens to the loose, powdery regolith, the soil, that covers the Moon's surface when shaking occurs on steep slopes. The South Polar region is not flat. It is a rugged landscape of deep craters with walls that rise steeply from permanently shadowed floors. The researchers found that some of these slopes are susceptible to landslides triggered by even, light seismic shaking, and the areas most vulnerable to landslides include some of the permanently shadowed regions that are of greatest scientific and practical interest, because they are the most likely locations for water ice deposits. This was a significant finding for the Artemis program. The whole point of going to the South Pole, the reason that region was selected over the equatorial sites visited by Apollo, is the potential for water ice in the permanently shadowed craters. But the ice sits in exactly the places that are most vulnerable to the seismic hazard created by the Moon's ongoing contraction. The resource and the risk are in the same location. Then the picture got larger. In December 2025, a team led by C.A. Naipova at the National Air and Space Museum's Center for Earth and Planetary Studies published the results of the first systematic global survey of a different class of tectonic features called small mare ridges. These are subtle geological structures found across the Maria, the vast dark plains that cover much of the Moon's near side. They form through the same compressive forces that create lobate scarps in the highlands, but they occur in a different geological setting, in the basalt-filled basins, rather than the ancient highland crust. What Naipova and colleagues found was that small mare ridges are everywhere, more than 1,000 of them, distributed across the lunar Maria on both the near side and the far side. They are geologically young. They are formed by the same contraction-driven forces that produce the lobate scarps, and their existence means that the Moon's tectonic activity is not confined to the highlands or the polar regions. It is global. That last point matters more than it might seem at first. When Waters discovered the lobate scarps in the highlands in 2010, it was possible to argue that the contraction-driven faulting was concentrated in certain regions and absent from others. The Maria, which are composed of younger basalts that filled ancient impact basins, might have responded differently to the contraction, absorbing the stress without breaking. The discovery of over 1,000 small mare ridges eliminates that possibility. The entire moon is contracting, the entire surface is subject to faulting, and every fault is a potential source of moonquakes, because both lobite scarps and small mare ridges form through the same mechanism, thrust faulting driven by global contraction. The quakes they produce would have the same characteristics as the shallow moonquakes recorded by Apollo. They would occur suddenly, without warning. They would generate shaking strong enough to disturb the surface, and because of the moon's rigid, dry interior, that shaking would persist for far longer than any comparable event on Earth. The implications for future exploration are direct. Any permanent structure on the moon, any base, habitat, or mining operation would need to account for the possibility of sustained seismic events that could last for tens of minutes or longer. The engineering challenge is not simply to build something that can withstand a brief jolt. It is to build something that can endure prolonged shaking on a surface made of loose, dry gravel that has no capacity to dampen the vibrations. NASA is aware of this. The Lunar Environment Monitoring Station, a payload co-led by Nicholas Schmer, is planned for deployment during the Artemis 3 mission. It would assess seismic risks at the South Polar Landing Site in real time, providing the first new seismic data from the moon in nearly 50 years. The Farside Seismic Suite, another NASA-supported instrument, is scheduled to be delivered to Schrödinger Basin on the far side of the moon as part of the Commercial Lunar Payload Services program. It will carry 2 sensitive seismometers to listen to the far side for the first time in history, filling a gap in coverage that has existed since the Apollo network was shut down. But for now, the gap remains. We know the moon is shrinking. We know the shrinking produces faults. We know the faults produce quakes. We know those quakes last far longer than their earthly counterparts. We have mapped over 1,000 new tectonic features in the last 2 years alone, and we know that the area selected for humanity's next visit to the moon sits in the middle of this activity. There is something worth pausing on here. The moon has been shrinking for hundreds of millions of years. The process is not accelerating. It is not approaching some catastrophic endpoint. The contraction is gradual, imperceptible on any human timescale, and the quakes it generates are infrequent. Thomas Waters himself has noted that the probability of a strong shallow moonquake occurring during a short mission like Artemis 3 is extremely low. The risk is real, but it is a risk measured in probabilities over long periods, not an imminent danger. The larger significance is not about immediate hazard. It is about what the shrinking tells us about the moon as a world. A body that is still contracting from interior cooling is a body that has not yet reached thermal equilibrium. Its internal processes are not finished. The engine that drove lunar geology for billions of years, the slow release of heat from the interior, is still running, weakly quietly, on a time scale that dwarfs human civilization, but running nonetheless. The moon is not dead. It is dying, very slowly, the way all rocky worlds eventually die as their internal heat bleeds away into space. But it is not dead yet, and the evidence of its remaining vitality is written in the faults and ridges and quakes that new instruments keep finding, year after year, in places nobody expected them to be. That ongoing interior cooling is responsible for more than just the shrinking and the quakes. It connects to something else, something that has been measured continuously and precisely for more than 50 years. Because while the moon contracts inward, pulled by the loss of its own heat, it is simultaneously drifting outward, pushed by a force that has nothing to do with its interior and everything to do with the planet it orbits. The moon is leaving. Slowly, imperceptibly, but measurably, it is moving away from Earth, and it has been doing so since the moment it was formed. The story of how we know this begins with a remarkably simple idea executed with extraordinary precision. During the Apollo 11 mission in July 1969, astronauts deployed a panel of retroreflectors on the surface of the Sea of Tranquility. The device had no electronics, no power source, no moving parts. It was simply an array of specially designed corner cube mirrors, each one engineered so that any beam of light striking its surface would be reflected directly back toward its source, regardless of the angle of incidence. The purpose was measurement. From Earth-based observatories, scientists began firing laser pulses at those mirrors and timing how long it took for the reflected light to return. Since the speed of light is known with exquisite precision, the round-trip travel time gives the distance between the observatory and the mirror to within a few centimeters. Additional retroreflector arrays were deployed by Apollo 14 and Apollo 15, and 2 more were placed by Soviet robotic landers, Lunokhod 1 and Lunokhod 2. Together, these 5 reflector sites created a network that allowed scientists to track the distance between Earth and the Moon continuously across decades, with an accuracy that has no parallel in the history of measurement. The results from this experiment, which has been running for more than 50 years and continues to operate today, tell a story that is both simple and profound. The Moon is moving away from Earth at an average rate of 3.83 centimeters per year. That is approximately 1.5 inches. It is roughly the rate at which your fingernails grow. It is, on any human timescale, undetectable without instruments, but it is relentless. It does not pause. It does not reverse. Year after year, orbit after orbit, the Moon drifts a tiny fraction further from the planet that created it. The mechanism driving this separation is the same one that has been influencing the Earth-Moon system since the Moon's formation approximately 4.5 billion years ago. It is tidal friction. Here is how it works. The Moon's gravitational pull raises bulges in the Earth's oceans. These are the tides. But because the Earth is rotating faster than the Moon is orbiting, the Earth's rotation carries those tidal bulges slightly ahead of the Moon's position. The bulge that faces the Moon is not directly beneath it. It is displaced forward in the direction of Earth's rotation by a small but significant angle. That displaced bulge has gravitational attraction of its own. It pulls on the Moon, and because it is positioned slightly ahead, the pull has a forward component, a gentle acceleration in the direction of the Moon's orbital motion. That acceleration adds energy to the Moon's orbit, and when you add energy to an orbit, the orbit gets larger. The Moon moves outward. The energy has to come from somewhere. It comes from Earth's rotation. The same tidal interaction that accelerates the Moon exerts a braking force on the Earth, slowing its spin by a tiny amount. The angular momentum of the system is conserved. Earth loses rotational energy. The Moon gains orbital energy. The days get longer. The Moon gets further away. The numbers are small on any human timescale, but they compound across geological time in ways that are stunning. Earth's rotation is currently slowing at a rate of approximately 2.4 milliseconds per century. That means every 100 years, the day gets about 2.5 thousandths of a second longer. You would never feel it. Your grandchildren's grandchildren would never feel it. But it is real, and it accumulates. Fossil evidence confirms that the accumulation has been ongoing for hundreds of millions of years. In the 1960s, paleontologist John Wells examined the growth rings of ancient coral fossils from the Devonian period, approximately 400 million years ago. Corals lay down daily and annual growth bands, much like tree rings, and by counting the number of daily bands within each annual cycle, Wells could determine how many days were in a year at the time the coral lived. His count showed approximately 400 days per year. Since the length of a year is determined by Earth's orbit around the Sun and has not changed significantly, more days per year means shorter days. The Earth was spinning faster 400 million years ago. Each day was roughly 22 hours long. Going further back, tidal rhythmites, layers of sediment deposited by tides and preserved in ancient rocks from approximately 620 million years ago, suggest that a day on Earth was roughly 21 to 22 hours long. and geological studies published in recent years, examining rocks from 3.2 billion years ago, calculate that the Earth-Moon distance at that time was about 70% of what it is today, and a single Earth day lasted only about 13 hours. This means the Moon has travelled an enormous distance since its formation. It is believed to have originated roughly 15,000 miles from Earth, the result of a cataclysmic collision between the young Earth and a Mars-sized body called Theia, approximately 4.5 billion years ago. The debris from that impact coalesced into the Moon, which at that distance would have appeared more than 15 times larger in the sky than it does today. The tidal forces at that proximity would have been extraordinary. The early Earth's day may have been as short as 4 or 5 hours. Since then, the Moon has spiralled outward to its current average distance of approximately 238,900 miles, and it continues to recede. The process will not stop until the Earth and Moon reach a state of tidal locking, where Earth's rotation period equals the Moon's orbital period. Models estimate that equilibrium would require roughly 50 billion years to achieve, at a mutual period of about 47 days. But the Sun will expand into a red giant in approximately 5 to 6 billion years, engulfing both Earth and the Moon long before tidal locking can be completed. The Moon will never actually leave us. It will still be slowly drifting outward when both bodies are consumed. There is one consequence of the recession that is more poignant than most. In about 600 million years, the Moon will have moved far enough away that it will no longer be able to completely cover the disk of the Sun as seen from Earth's surface. Total solar eclipses will end. The alignment that allows the Moon to perfectly block the Sun, producing the corona, the diamond ring effect, and the eerie darkness of totality, is a coincidence of the present era. The Sun is about 400 times larger than the Moon, but also about 400 times farther away, which makes them appear almost exactly the same size in the sky. That is not a permanent condition. It is a temporary geometric accident, and it is one that will slowly dissolve as the Moon continues its outward drift. Now, there is something worth noting about the recession rate. The current rate of 3.83 centimeters per year, if projected backward in time at a constant value, would place the Moon in contact with Earth only about 1.5 billion years ago. That is obviously incorrect. The Moon is roughly 4.5 billion years old, and it existed as a distinct body long before 1.5 billion years ago. The resolution to this apparent paradox is that the recession rate has not been constant. It depends on the specific arrangement of Earth's continents, the depth and shape of the ocean basins, and the resonant properties of the tidal system at any given time. When the continents are arranged in a way that amplifies tidal dissipation, the Moon recedes faster. When the arrangement is less effective at dissipating tidal energy, the rate slows. The current rate is unusually high by geological standards. The present configuration of the continents, with narrow ocean basins like the Atlantic that amplify tidal resonance, produces more tidal friction than most configurations in Earth's history. In the deep past, the recession was likely much slower for extended periods, which is consistent with the Moon being 4.5 billion years old despite the current high rate of retreat. This detail connects back to the reference point you may recall from earlier in this conversation about the forces acting on Earth's rotation. The tidal interaction between the Earth and Moon is the same force that is gradually slowing Earth's spin. It is the same force that contributed to the ancient coral having 400 days in a year. And it is one of the same forces, tidal stress from Earth, that contributes to the moonquakes detected by the Apollo seismometers. The Moon's slow departure from Earth is not a separate story from the shrinking and the quaking. It is part of the same gravitational conversation that has been ongoing between these two bodies for 4.5 billion years. But there is something else happening to the Moon as it drifts away and slowly contracts, something that was discovered not by seismometers or laser reflectors but by spacecraft carrying spectrometers and radar systems designed to examine the composition of the lunar surface. For decades, the moon was considered the driest object in the solar system. Every sample brought back by the Apollo astronauts appeared to contain no water whatsoever. The assumption was universal and seemed obvious. No atmosphere means no rain. No rain means no water cycle. No magnetic field means the solar wind would strip any volatile compounds from the surface. The moon, by every line of reasoning available, should have been completely and permanently dry. Then in 2008, India launched a spacecraft called Chandrayaan-1, and everything changed. Chandrayaan-1 was India's first mission to the moon, and it carried instruments from multiple space agencies, including 2 from NASA. One was called the Moon Mineralogy Mapper, or M3, an infrared spectrometer designed to identify the chemical composition of the lunar surface by analysing how it absorbed and reflected sunlight at different wavelengths. The other was the Miniature Synthetic Aperture Radar, or MINI-SAR, a lightweight instrument designed to peer into permanently shadowed craters using radar pulses. The results from both instruments were extraordinary. M3 detected absorption features near 2.8 to 3.0 micrometers across broad areas of the lunar surface, a spectral signature that is characteristic of either water molecules or hydroxyl groups, which are fragments of water molecules bonded to minerals. The detection was not limited to the poles. It appeared at multiple latitudes, suggesting that a thin layer of water or hydroxyl was present across much of the moon's surface, probably created by the interaction between the solar wind's hydrogen ions and oxygen in the lunar soil. MINI-SAR went further, peering into the permanently shadowed craters at the lunar North Pole with radar. It found reflections consistent with the presence of water ice in more than 40 craters, with crater diameters ranging from about 2 to 15 kilometers. The radar signatures did not prove ice, beyond all doubt, as other materials can produce similar reflections under certain conditions, but the pattern was suggestive and consistent with what scientists would expect if water ice had accumulated in locations where the sun never reaches. In October 2009, NASA pushed the evidence further with a dramatic experiment. The Lunar Crater Observation and Sensing Satellite, known as ELSI-ROSS, deliberately crashed a Centaur rocket stage into Cabeus crater at the moon's south pole. The impact struck with tremendous force, excavating material from the crater floor and lofting it in a plume that rose above the crater wall into sunlight. A trailing Shepard spacecraft flew through the plume, analysing its composition with a suite of spectrometers. The results were definitive. The plume contained water, not traces or ambiguous signals, but confirmed water ice and water vapour, along with other volatile compounds including methane, ammonia, hydrogen sulfide and carbon dioxide. NASA announced that the El-Crocess impact had confirmed the presence of water ice in the permanently shadowed regions of the lunar South Pole. The bone-dry moon contained water, and it had been there, frozen in the perpetual darkness, likely for billions of years. The discoveries did not stop. In 2018, a comprehensive reanalysis of the M3 data confirmed 3 distinct near-infrared absorption peaks at 1.3, 1.5 and 2.0 micrometers at both the north and south poles. These 3 peaks together constitute the unique spectral fingerprint of water ice, not hydroxyl, not hydrated minerals, but actual frozen water on the lunar surface. The paper was published in the Proceedings of the National Academy of Sciences, and it settled the debate that had been simmering for a decade. Water ice exists on the moon. The question was no longer whether it was there, but how much of it there was and whether it could be accessed. Then in 2020, a detection was made that expanded the picture yet again. An instrument called the Faint Object Infrared Camera for the SOFIA telescope, mounted on a modified Boeing 747 aircraft that flew above most of the Earth's atmospheric water vapour to observe in the infrared, detected the 6 micrometer emission, bound from a region near Clavius crater, in the Moon's southern hemisphere. This wavelength is the unique radiation signature of molecular water, distinguishable from hydroxyl and from any mineral that merely contains oxygen-hydrogen bonds. The finding, published in Nature Astronomy by Casey Honeyball and colleagues, confirmed that water molecules exist even on sunlit regions of the Moon. The concentrations were tiny, roughly 100 to 400 micrograms per gram of soil, equivalent to about a 12-ounce bottle of water spread across a cubic metre of lunar surface material. But the significance was not the quantity, it was the implication. If water molecules could persist on sunlit surfaces where temperatures reached 250 degrees Fahrenheit during the lunar day, then the processes creating or depositing water on the Moon were more active and more widespread than anyone had assumed. The most recent chapter in this story was written by India's Chandrayaan-3 mission, which landed near the Moon's south pole in August 2023. The Vikram lander carried an instrument called the Chandra Surface Thermophysical Experiment, or CHASTE, essentially a precision thermometer designed to measure temperatures at the surface and at depths up to 10 centimetres below it. This was the first time in situ thermal measurements had been taken at high lunar latitudes. The Apollo missions had measured temperatures only at equatorial sites, and orbital instruments could only estimate temperatures from a distance. CHASTE provided ground truth. What the instrument found was surprising. Even within a single metre of the landing site, temperatures varied dramatically depending on the slope and orientation of the surface. A sun-facing slope inclined at just 6 degrees recorded a peak temperature of 82 degrees Celsius during the lunar day and dropped to minus 168 degrees Celsius as lunar night approached, but a flat region only 1 metre away recorded a significantly lower peak of 59 degrees Celsius. The local topography, even at scales of a single step, created wildly different thermal environments. The research team, led by Durga Prasad of the Physical Research Laboratory in Ahmedabad, used these measurements to build a model of lunar surface temperatures that accounted for slope angle and orientation. The model's conclusion, published in Communications, Earth and Environment in early 2025, was significant. Slopes greater than 14 degrees that face away from the sun at high latitudes, between 60 and 80 degrees north or south, could be cold enough to harbour water ice at depths of just a few centimetres below the surface. These areas receive some sunlight and are not permanently shadowed, but their temperatures remain low enough that ice, once deposited, could persist. This finding expanded the potential water-bearing territory on the Moon far beyond the permanently shadowed craters that had been the exclusive focus of previous research. If ice exists in these high latitude slopes, it would be vastly more accessible than ice buried in the pitch-black, rugged interiors of polar craters. An astronaut or a robotic system could potentially reach these ice deposits without having to navigate into permanently shadowed regions where temperatures drop below minus 230 degrees Celsius and no solar power is available. The race to confirm and characterize these deposits is now fully underway. China's Chang'e 7 mission, scheduled to launch in August 2025, will explore the area around Shackleton Crater at the lunar South Pole. The mission will carry an orbiter, a lander, a rover, and a small hopping robot designed to enter permanently shadowed regions. Its primary scientific objective is to search for the water ice. A team of researchers recently published a thermal model of Shackleton Crater, specifically to guide Chang'e 7's exploration, identifying the locations within and around the crater where water ice is most likely to be preserved. NASA's own Viper rover, designed specifically for ice prospecting, has been through a complicated development history, but represents the agency's commitment to answering the same question from a different direction. The Artemis program itself, beyond its historical and political significance, is fundamentally structured around the premise that the Moon's south polar ice deposits are a viable resource, and the reason that matters is not just scientific. Water ice on the moon is the single most valuable resource for sustained human space exploration. Water can be split into hydrogen and oxygen through electrolysis. The oxygen becomes breathable air. The hydrogen and oxygen together become rocket propellant. Water itself is obviously essential for drinking and for growing food. If the moon's ice deposits prove to be substantial and accessible, they transform the moon from a scientific destination into an operational base, a place where missions can refuel, resupply and extend their reach toward Mars and beyond without having to carry everything from Earth. The irony is that the ice exists precisely because the moon is dead in certain ways. It has no atmosphere to redistribute volatile compounds. It has no magnetic field to deflect the solar wind, which is one of the mechanisms that delivers hydrogen to the lunar surface in the first place. The permanently shadowed craters maintain their extreme cold because the moon has no weather, no atmospheric circulation, no mechanism to transport heat from sunlit regions to shadowed ones. The silence and stillness that make the moon inhospitable are the same conditions that preserve the one resource, capable of making it useful. But there is a tension in this picture. The ice sits in permanently shadowed regions and on cold, steep slopes. The moonquakes generated by the moon's ongoing contraction threaten exactly those locations with landslides and surface disturbance. The resource and the hazard are intertwined. Understanding both, mapping the ice and mapping the faults, is now a priority for every agency planning to return humans to the moon. And there is still more to the moon story. The water, the quakes, the shrinking and the drift are all things happening to the moon now, or in the geologically recent past. But to fully understand what is happening to this world, you need to go back further, much further, to a time when the moon was not a quiet, dead-looking companion, but a world with a magnetic field, powerful enough to rival Earth's own, generated by the same kind of churning liquid core that protects our planet from the radiation of space. A field that at some point died, leaving the moon exposed to the full bombardment of the solar wind. The story of how and when that field disappeared is one of the most debated questions in planetary science, and the answer keeps changing as new evidence arrives. To understand what the moon lost, you first have to understand what Earth has. Right now, as you listen to this, the planet you are lying on is wrapped in an invisible shield, generated roughly 1,800 miles beneath your feet. Earth's outer core is a churning ocean of liquid iron, heated from below by the solid inner core and cooled from above by the mantle. That temperature difference drives convection. The liquid metal rises, falls and circulates in vast columns that are twisted by the planet's rotation into spiraling patterns. Those moving currents of electrically conductive fluid generate a magnetic field through a process called the geodynamo, the same fundamental physics that allows a spinning coil of wire to generate electricity in a power plant. Earth's magnetic field extends outward from the core, through the mantle, through the crust and out into space, forming a bubble called the magnetosphere that deflects charged particles streaming from the sun. Without it, the solar wind would gradually strip away the atmosphere and bathe the surface in radiation. Mars once had a magnetic field. It lost its field billions of years ago, and over time the solar wind eroded much of its atmosphere. Today Mars has an atmospheric pressure less than 1% of Earth's and no liquid water on its surface. The magnetic field is, in a very real sense, the reason Earth is livable. The moon once had one too. The evidence came from the rocks that Apollo astronauts brought home. When lava erupts and cools into rock, the tiny magnetic minerals within it, grains of iron oxide and other magnetically sensitive compounds, align themselves with whatever magnetic field exists at that location and at that moment. As the rock solidifies, the alignment freezes in place. It becomes a permanent record of the field that existed when the rock formed, a kind of geological compass needle locked in stone. When scientists at MIT and elsewhere analysed the magnetic signatures in Apollo samples, they found something remarkable. Some of the oldest lunar rocks, those dating to approximately 4 billion years ago, recorded a magnetic field of roughly 100 microteslas. To put that in context, Earth's magnetic field at the surface today measures between 25 and 65 microteslas, depending on location. The Moon, 4 billion years ago, had a magnetic field that may have been roughly double the strength of Earth's current field. That field had to have come from a dynamo. The only known mechanism capable of generating a sustained planetary scale magnetic field is the convection of liquid metal in a planetary core. The Moon, at the time those rocks formed, must have had a liquid metallic core undergoing vigorous convection. Benjamin Weiss, a professor of Earth, atmospheric and planetary sciences at MIT, has been studying the lunar magnetic field for years. His group's work, along with contributions from researchers around the world, has assembled a timeline that traces the rise and fall of the lunar dynamo across billions of years. The picture they have constructed is both fascinating and contested. The strong field phase appears to have lasted from roughly 4.25 billion years ago to about 3.56 billion years ago. During this period, the Moon's field was comparable to, or stronger than, Earth's present field. The leading explanation for what powered the dynamo during this early phase is the gravitational influence of Earth itself. When the Moon was young, it orbited much closer to Earth than it does now. At that proximity, Earth's tidal forces would have been strong enough to physically stir the Moon's liquid core, driving the convective motions that generated the field. This is called a tidally driven dynamo, and it is a mechanism that would have weakened steadily as the Moon spiraled outward and the tidal forces diminished. By approximately 3.5 billion years ago, the field had weakened significantly. In 2017, Weiss and his colleagues found evidence from a lunar rock sample that the field had dropped to roughly 10 microteslas by about 2.5 billion years ago, a fraction of its earlier strength. The tidal mechanism had run out of energy as the Moon's distance from Earth increased, but the field had not completely disappeared. Something else was sustaining it, albeit weakly. The most likely candidate for this later stage power source is core crystallization. As the Moon's interior continued to cool over billions of years, the innermost part of the liquid core began to solidify. When iron crystallizes out of a liquid metal solution, it releases lighter elements and latent heat. Both of these drive convective currents in the remaining liquid, stirring the core in the same way that the tidal mechanism had stirred it earlier, though with less vigor. The result was a weaker but persistent magnetic field that continued to operate even after the tidal driving force had faded. Then at some point the dynamo stopped entirely. Weiss and his team, in a study published in Science Advances in January 2020, analysed 2 lunar rock samples that had been reheated by a major impact approximately 1 billion years ago. The reheating erased their original magnetic record and allowed them to record whatever field existed at the time of the impact. When the researchers measured the magnetic signature in these samples, they found a field strength of no more than 0.1 microteslas, so weak that Weiss concluded the dynamo had likely ceased by that time. The picture that emerged from this work was relatively clean, a strong dynamo powered by tidal forces until about 3.5 billion years ago. A transition to a weaker dynamo powered by core crystallization until approximately 1 to 1.5 billion years ago. Then silence. The core fully crystallized, the convection stopped, the field collapsed and the Moon was left without a magnetic shield. But science does not stay clean for long. In 2024, a study led by John Tarduno and colleagues published in Communications, Earth and Environment challenged the timeline, using a technique called single crystal paleointensity, which measures the magnetic record of individual mineral crystals rather than bulk rock samples. Tarduno's team analysed some of the same Apollo rocks that had been used to establish the strong field era. Their results were dramatically different. The individual crystals showed no evidence of a strong magnetic field. The team concluded that the Moon may not have had a long-lived core dynamo at all, and that if one existed it was limited to the Moon's first approximately 140 million years, far shorter than the previous estimates of billions of years. The strong magnetic signals detected in earlier whole rock studies, Tarduno argued, may not have been recording a core dynamo. They may instead have been the result of impact processes, the intense but brief magnetic fields generated by the plasma created during large asteroid impacts. These impact-generated fields could have been strong enough to magnetize the rocks without any core dynamo being active at the time. This was a direct challenge to the established narrative. If the dynamo lasted only 140 million years, then for most of the Moon's history, it has been essentially unshielded. The implications for the lunar surface are significant. Without a magnetosphere, the solar wind has been directly impacting the lunar regolith for over 4 billion years, implanting hydrogen atoms, eroding the surface and modifying its chemistry. Then, in early 2025, a study based on samples returned by China's Chang'e 5 mission added another twist. The Chang'e 5 basalt, which is approximately 2 billion years old, the youngest lunar basalt ever returned to Earth, showed weak but detectable paleo-intensities of roughly 2 to 4 microteslas. This suggested that some form of dynamo was still active at 2 billion years ago, supporting the core crystallization model and contradicting Tarduno's claim that the dynamo died within the first 140 million years. And in February 2026, a paper published in Nature Geoscience proposed yet another possibility. The dynamo, the researchers argued, may have been intermittent. They found a statistically significant correlation between recovered magnetic field strengths and the titanium content of lunar basalts. Their model suggested that episodic eruptions of titanium-rich magma rising from deep in the mantle could have extracted heat from the core impulses, temporarily restarting the dynamo for brief periods of perhaps a few thousand years at a time. Between these episodes, the field would have been weak or absent. The strong signals recorded in some Apollo rocks would represent these brief flickers, not a sustained field. The honest summary of where this science stands right now is that the Moon's magnetic history is one of the most actively debated topics in planetary science. The community agrees on certain things. The Moon once had a magnetic field. That field was at some point strong. It eventually died. The Moon today has no global magnetic field, only localized anomalies, patches of rock on the surface that still carry the frozen remnant of whatever field existed when they last cooled. But the questions of when the field was strongest, how long it lasted, what powered it, and whether it was continuous or intermittent are still being argued. Each new study, each new technique applied to the limited collection of lunar rocks and the expanding set of return samples shifts the picture in one direction or another. What is not debated is the consequence of the field's absence. Without a magnetic shield, the Moon's surface is fully exposed to the solar wind. Charged particles from the Sun impact the regolith continuously, sputtering atoms from the surface, implanting hydrogen and helium, and creating a harsh radiation environment that any future human inhabitants would need to contend with. The radiation dose on the lunar surface is significantly higher than on the surface of Earth, and during solar particle events, storms of high-energy protons ejected by the Sun, it can spike to levels that are dangerous, even for short-term exposure. The lack of a magnetic field also connects to the water story. One of the proposed mechanisms for creating water on the lunar surface involves the solar wind itself. Hydrogen ions from the solar wind strike the oxygen-rich minerals in the lunar soil and form hydroxyl and water molecules. If the Moon had retained a magnetic field, those hydrogen ions would have been deflected away from the surface, and this source of water would not exist. The Moon's magnetic death, paradoxically, may be one of the reasons water can form on its surface. There is one more dimension to the magnetic story that deserves mention. The localized magnetic anomalies that persist on the Moon's surface, patches where the crustal rocks still carry a detectable magnetic signature, are not random. They tend to be concentrated in certain areas, and some of the strongest anomalies are found on the far side of the Moon, directly opposite some of the largest impact basins on the near side. One hypothesis is that these anomalies were created when the shock waves from massive impacts converged on the antipodal point, concentrating energy and magnetic material in a specific region. Another is that they are simply the remnants of whatever field existed when the rocks in those areas last cooled. Either way, the magnetic patches are interesting for future exploration. They provide slightly elevated protection against charged particles in their immediate vicinity, creating small zones where the radiation environment is marginally less harsh than the surrounding terrain. Whether these zones are large enough or protective enough to be practically useful for human activities remains an open question. The dynamo is dead. The field is gone. The moon's surface has been exposed to the raw solar wind for at least 1 billion years, and possibly much longer. But the interior that once generated that field is the same interior that is still cooling, still contracting, still producing the faults and quakes and ridges that we have been tracing throughout this conversation. The death of the dynamo and the ongoing geological activity are both expressions of the same underlying process, the slow loss of heat from the moon's interior. And there is one more expression of that process that we have not yet fully explored, something that has been observed from Earth for over 800 years, something that modern instruments are only now beginning to explain. Flashes of light on the lunar surface, brief, unpredictable, and coming from a world that by every conventional measure should not be producing them. To understand what those flashes are, and why they might be connected to everything else we have discussed tonight, we need to look at one of the oldest and strangest mysteries in lunar science. On the evening of June 18th, 1178, 5 monks at Canterbury Cathedral in England were observing the sky when they witnessed something that they described in terms so vivid that the account has survived intact for nearly 850 years. The chronicler Gervase of Canterbury recorded their testimony. They reported that as they watched the crescent moon, its upper horn suddenly split in two. From the midpoint of the division, a flaming torch sprang up, spewing fire, hot coals and sparks over a considerable distance. The body of the moon below, they said, writhed as if in anxiety, throbbing like a wounded snake. The phenomenon repeated 12 times or more before the moon resumed its normal appearance. That is colourful, unscientific language, but it is widely believed to be one of the earliest documented observations of what scientists now call a transient lunar phenomenon, or TLP. The term was coined in 1968 by the British astronomer Sir Patrick Moore, who had been observing the lunar surface for decades and had personally witnessed several unexplained visual changes on the moon's face. Moore co-authored a NASA technical report that same year, NASA Technical Report HAR 277, which compiled a chronological catalogue of reported lunar events from 1540 to 1966. The catalogue documented hundreds of observations from astronomers and casual observers around the world. People had been seeing strange things on the moon for centuries, brief flashes of light, temporary glows persisting for minutes or hours, colour changes, usually described as reddish, appearing over specific craters, mist or hazes that obscured surface detail that was normally visible, temporary brightenings in areas that should have been in shadow. The reports were not taken particularly seriously for most of that history. The moon was considered geologically dead. If nothing was happening on its surface, then anything people claimed to see must have been an atmospheric effect, an optical illusion, or simply an error in observation. The scientific establishment was not hostile to the reports, it was indifferent. TLPs were filed in the same mental category as UFO sightings, interesting as social phenomena, but not as physical ones. That changed gradually as the observations accumulated and certain patterns emerged. TLPs were not randomly distributed across the lunar surface, they clustered around specific locations. The Aristarchus crater region, a bright geologically complex area on the moon's near side, was the most frequently reported source. Plato crater was another. These were not arbitrary locations. They were areas of known geological interest, younger formations, regions with higher concentrations of radioactive elements, places where the crust might be thinner or more fractured than average. The clustering was suggestive. If TLPs were purely atmospheric artifacts or observer errors, They should have been scattered randomly. The fact that they concentrated around specific geological features on the moon hinted at a physical process originating from the moon itself. In the decades since Moore's catalogue, the study of TLPs has split into two distinct branches, based on the duration of the events. Short duration events, those lasting less than a minute, are now well understood. They are meteoroid impacts. The moon has no atmosphere. On Earth, small pieces of space debris burn up in the atmosphere long before reaching the surface. We see them as shooting stars. On the moon, there's nothing to slow them down or vaporize them. A rock the size of a billiard ball, weighing roughly half a pound, strikes the lunar surface at speeds that can exceed 40 miles per hour. The kinetic energy of that impact is converted instantaneously into heat and light. The surface material at the impact site is vaporized and briefly glows at temperatures high enough to be visible from Earth through a telescope. These impact flashes have been systematically recorded by dedicated monitoring programs. The European Space Agency funded the Near-Earth Object Lunar Impacts and Optical Transients project known as NELIOTA, which operated from 2017 to 2024 using a 1.2 metre telescope at the National Observatory of Athens. Over its operational period, NELIOTA recorded 193 confirmed lunar impact flashes. Each flash corresponded to a meteoroid strike, and the data has been used to improve estimates of the meteoroid flux in near-Earth space, information that is directly relevant to the safety of spacecraft and astronauts. In October and November of 2025, Japanese astronomer Daiichi Fuji, curator of the Hiratsuka City Museum, recorded 2 bright impact flashes within 48 hours, using specialized telescopes equipped with motion detection software. One flash appeared east of Gassendi crater on October 30th. The other appeared west of Oceanus Procellarum on November 1st. These observations added to a growing catalogue that demonstrates how frequently the moon is struck by debris and how routine these impacts are in the context of the broader solar system. A 2024 study co-authored by Alexios Liakos, the principal investigator for NELIOTA, analysed the distribution of recorded impact flashes and concluded that the moon is bombarded almost homogeneously across its surface. Earlier suggestions that impacts clustered in certain areas, particularly the Oceanus Procellarum region, were attributed to observational bias, the simple fact that telescopes tend to be pointed at certain regions more often than others. So the short duration flashes are explained. They are meteoroid impacts, happening constantly, detectable from Earth and posing a real but quantifiable risk to future lunar operations. A future base on the moon would need to account for the continuous bombardment of small debris, much as the International Space Station accounts for micrometeoroid risk in Earth orbit. But the longer duration TLPs, the ones that last minutes or hours, the glows and colour changes and hazes, these are a different matter entirely. They cannot be explained by meteoroid impacts. An impact flash is over in a fraction of a second. Something that glows for an hour requires a sustained energy source, and that energy source must come from within the moon. The leading hypothesis for these longer events is outgassing. The idea is that gas trapped within the lunar crust, accumulated over time through radioactive decay or other processes, is occasionally released through fractures and vents in the surface. The gas most commonly implicated is radon, a radioactive noble gas produced by the decay of uranium and thorium in the lunar rock. Radon is unstable and decays through a series of steps that include the emission of alpha particles. In a near-vacuum environment like the moon's surface, a cloud of radon gas released through a crack could produce a faint glow as the atoms decay. Supporting this hypothesis is a pair of studies published in the Astrophysical Journal in 2009 that found a spatial correlation between reported TLP sites and areas of elevated radon concentration detected by orbital instruments. The overlap is suggestive. Areas where gas is being released from the interior tend to be the same areas where observers have reported seeing transient glows and colour changes. If the outgassing hypothesis is correct, it connects TLPs directly to the tectonic activity we discussed earlier. The moon is contracting. The contraction produces faults. The faults crack the crust, and those cracks provide pathways for trapped gas to escape from the interior. The process would not be continuous. It would be episodic, occurring when tectonic stresses open new fractures or when tidal forces from Earth momentarily widen existing ones. The gas would escape in bursts, producing brief, localized glows that would be visible from Earth under the right conditions. This is speculative. The outgassing hypothesis has not been definitively proven. The evidence is circumstantial. A spatial correlation between TLP reports and radon-rich areas, a physically plausible mechanism, and a theoretical connection to known tectonic processes. But no TLP has ever been observed simultaneously by multiple independent observers using calibrated instruments in a way that would allow the spectrum of the glow to be analysed in real time. The events are too brief, too unpredictable, and too faint for most modern observatories to catch. There are efforts to change that. Hakan Kayal, a professor of space technology at Julius-Maximilians-Universität Würzburg in Germany, has built a dedicated lunar monitoring telescope designed to detect and automatically record TLP events. The system uses cameras with different filters to capture colour information and is designed to alert the operator when an anomalous event is detected, allowing follow-up observations before the event fades. If a TLP can be caught in the act and its spectrum analysed, scientists could determine whether the glow is consistent with radon decay, with electrostatic effects in the lunar dust, or with some other mechanism entirely. The electrostatic hypothesis is worth mentioning briefly. The lunar surface, lacking an atmosphere and exposed to the solar wind and ultraviolet radiation, becomes electrically charged. The boundary between sunlit and shadowed terrain, the terminator, is a region of particularly strong charge gradients. Some researchers have proposed that these charge differences could cause dust particles to loft above the surface, creating a faint haze visible under certain lighting conditions. This mechanism could explain some of the haziness and obscuration reported in TLP observations, particularly those observed near the terminator. There is also a more exotic possibility that has been discussed in the literature, though not widely accepted. Residual volcanic activity, not full-scale eruptions. The moon's volcanism ended hundreds of millions of years ago, but minor degassing, events associated with the last traces of thermal activity in the deep interior. The boundary between the possible and the implausible here depends entirely on how much residual heat the moon's interior retains, and that question, as we have discussed, is still being investigated. What can be said with confidence is this: the moon produces visual phenomena that cannot all be explained by external impacts. Some of them appear to originate from internal processes. Those internal processes are most likely connected to the same tectonic and thermal forces that produce the faulting, the quaking, and the contraction. The flashes are not a separate mystery. They are another symptom of the same underlying condition, a world that is still cooling, still cracking, and still releasing the remnants of its internal energy into the vacuum above. Over 3,000 TLP events have been catalogued in the last 2 millennia. The vast majority are unconfirmed in the scientific sense. They were reported by individual observers without corroborating data, but the sheer volume of reports, their concentration around geologically significant locations, and their consistency with known lunar processes are enough to keep the scientific community interested. TLPs are not fringe science. They are a recognised category of lunar observation, with a dedicated research community, published journals and active monitoring programs. The Canterbury monks in 1178 did not know what they were seeing. They described it in the language available to them: fire and sparks and the throbbing of a wounded snake. 847 years later, we have spectrometers, orbital cameras, laser reflectors, and decades of seismic data, and we still cannot fully explain what they saw, but we are closer. And every new instrument we send to the moon brings us closer still. Now, we have traced the moon's story from its trembling interior to its cracking surface, from its ancient magnetic field to its modern-day flashes, from its slowly receding orbit to its hidden reserves of ice. Each of these threads has been presented as a separate discovery, but they are not separate. They are all expressions of the same reality. The moon is a world in the middle of a transition that has been going on for billions of years and will continue for billions more. And when you lay all of these signals on top of each other and look at the aggregate picture, something becomes clear that is not obvious when you examine any one of them in isolation. The moon is not a collection of unrelated phenomena. It is a connected system, and the connections matter. To see those connections, you need a picture of the moon's interior, not the simple diagram from a textbook, a sphere with 3 neat layers coloured in different shades, but the real thing, as far as we understand it from the Apollo seismic data and the decades of modelling that followed. The moon's outermost layer is the crust. It is not uniform. On the near side, the side that always faces Earth, the crust averages roughly 40 miles thick. On the far side, it is significantly thicker, reaching 60 miles or more in places. This asymmetry, the fact that the far side's crust is roughly 50% thicker than the near side's, is one of the moon's most enduring puzzles. The leading explanations involve the early tidal interaction with Earth, the distribution of heat-producing radioactive elements, and the pattern of ancient impacts that created the great basins now filled with dark basalt on the near side. Beneath the crust lies the mantle, a thick layer of silicate rock that extends downward for roughly 800 miles. The upper mantle is rigid. The deeper mantle becomes more plastic, more willing to flow slowly under sustained pressure, though it is not liquid in any conventional sense. It is solid rock that behaves, over millions of years, more like an extremely viscous fluid. And at the very centre sits the core. In 2011, a study led by Renee Weber at NASA's Marshall Space Flight Center used sophisticated reanalysis of Apollo seismic data to construct the most detailed picture yet of the moon's deep interior. Weber's team found evidence for a layered core. The innermost part is a solid iron core with a radius of roughly 150 miles. Surrounding it is a fluid outer core of liquid iron, roughly 55 miles thick. And surrounding that is a partially molten boundary layer where the lower mantle transitions from solid to fluid, a zone roughly 90 miles thick with properties intermediate between the core and the overlying mantle. This structure is broadly similar to Earth's layered core, solid inner iron surrounded by liquid outer iron, but at a dramatically smaller scale. Earth's core is roughly 2,200 miles in radius. The moon's is roughly 200 miles. The moon's core accounts for a much smaller fraction of its total volume than Earth's does, which is one reason the moon's density is lower and its gravitational field is weaker. The connection between this interior structure and everything happening at the surface runs through a single physical process: thermal evolution. The moon is cooling. It has been cooling since its formation. The rate of cooling depends on the size of the body, its composition, and the efficiency with which heat can be transported from the interior to the surface and radiated into space. Smaller bodies cool faster than larger ones because they have a higher ratio of surface area to volume. The moon, being much smaller than Earth, has cooled much more rapidly. Its core has largely or entirely solidified. Its mantle has become rigid enough that it no longer flows easily. And as the interior has cooled and contracted, the rigid crust above has broken under the compression, producing the faults and scarps and ridges that we have been discussing. The dynamo died because the cooling killed it. A magnetic field requires convection in a liquid metallic core. When the core solidifies, the convection stops. When the convection stops, the field collapses. The timeline of the dynamo's death corresponds to the timeline of core cooling. Whether that death occurred 1 billion years ago or 4.3 billion years ago, as the competing studies suggest, the mechanism is the same. The core ran out of energy to sustain convective motion and the field switched off. The faulting occurs because the cooling produces volume change. Thermal contraction of the deep interior reduces the moon's overall radius, but the crust, already cold and rigid, cannot shrink smoothly to accommodate the reduced volume beneath. It breaks. The pattern of faulting is global because the cooling is global. Every part of the interior is losing heat, and every part of the crust is responding to the resulting compression. The moon quakes are the sound of that breaking. When compressive stress along a fault exceeds the strength of the rock, the fault slips suddenly, releasing energy as seismic waves. The sustained duration of the shaking reflects the lack of dampening mechanisms in the lunar interior. No water, no fluid outer core, no atmosphere. The energy bounces and reverberates through the rigid body until friction within the rock eventually absorbs it. The outgassing that may produce some TLPs is a byproduct of the same interior activity. Radioactive elements in the crust and mantle produce gaseous decay products, principally radon. These gases migrate through pores and fractures in the rock. When tectonic activity creates new fractures or momentarily widens existing ones, the accumulated gas can escape to the surface in a burst. The contraction drives the faulting. The faulting opens the pathways, and the gas escapes through them. The water ice in the polar craters is connected through a different chain of causation, but still links back to the moon's overall state. The ice is preserved because the moon lacks an atmosphere, a magnetic field, and significant tectonic activity at the surface. All three of those absences are consequences of the cooling. The atmosphere was never substantial to begin with, but whatever volatile inventory the moon once possessed has been lost because the weak gravity and the absence of a magnetic field left the surface exposed to solar wind erosion. The magnetic field died because the core cooled. The surface remains relatively undisturbed at the poles because the faulting, while global, is not violent enough or frequent enough to have overturned the entire surface. The ice that accumulated in the permanently shadowed craters from comet impacts, volcanic outgassing and solar wind interactions has been able to persist precisely because the moon is quiet enough to preserve it. And the recession from Earth, the slow outward drift measured by the laser reflectors, ties into the story through the tidal forces that connect the two bodies. Those forces contribute to the moonquakes by stressing the lunar crust. The deep moonquakes recorded by Apollo, the ones originating 700 to 1,100 kilometers down, were tidally driven, produced by the rhythmic flexing of the moon's interior as it orbits Earth. The same tidal forces that are pushing the moon away are squeezing and releasing its interior on every orbital cycle, generating the most common type of seismic activity observed. When you see all of this together, the moon stops looking like a dead rock with a few interesting features. It looks like a machine in the middle of winding down. Every gear is still turning, just more slowly. The heat engine that powered its volcanism, its magnetic field and its tectonic activity is running on its last reserves of thermal energy. The output of that engine is no longer dramatic. There are no eruptions, no global field, no rapid surface reshaping, but there are quakes, cracks, gas releases, flashes, and a slow, geometric contraction that is detectable from orbit. The moon is not dead. It is in the late stages of a process that every rocky world in the solar system eventually undergoes. Mercury is further along that process. It is smaller than the moon's diameter, but more massive due to its enormous iron core, and it has shrunk far more dramatically. Mercury's thrust faults are up to 600 miles long and over a mile high, orders of magnitude larger than the moon's lobatic scarps. Mercury's contraction has been more violent and more extensive because its core is larger relative to its total size, and the thermal evolution has been more extreme. Mars is at a different point in the same process. It lost its magnetic field approximately 4 billion years ago. Its volcanism persisted more recently, with evidence suggesting that some volcanic activity may have occurred within the last few 100 million years, but it is now largely quiescent. Its surface is heavily faulted, Its atmosphere has been partially stripped, and its water, once abundant, is now largely frozen underground. Earth is the outlier. Earth's core is still vigorously convecting. Its magnetic field is strong and active. Its volcanism is ongoing. Its tectonic plates are in constant motion. Earth has not worn down because it is larger, retains more internal heat, and has a core that is still far from fully crystallized. But Earth is also cooling. The same process that silenced the moon's dynamo and is slowly contracting its surface is operating on Earth, just at a much slower rate. Earth's day is getting longer. Its magnetic field fluctuates, and in the very deep future, measured in billions of years, Earth's core too will eventually solidify. Its magnetic field will die, and its tectonic activity will cease. The moon is a preview, a small nearby example of where every rocky world eventually ends up. This perspective is what makes the moon scientifically invaluable, beyond its practical utility as a source of ice or a platform for astronomical observations. It is a case study in planetary death. It shows how a world transitions from geologically active to geologically quiescent. By studying the moon's faults, its magnetic remnants, its seismic activity, and its thermal profile, scientists can test models of planetary evolution that apply not just to the moon but to every rocky body in the solar system and beyond. The data gathered by the Apollo seismometers in the 1970s was foundational, but it was also limited. The network consisted of only 4 stations, all clustered in a relatively small region on the near side of the moon. It operated for just 8 years. The instruments were state-of-the-art for their time, but would be considered crude by modern standards. The seismic signals were coarsely digitized, the bandwidth was limited, and the spatial resolution was poor. Despite those limitations, the Apollo seismic data remains the only comprehensive seismic dataset from any extraterrestrial body. No other planet or moon has been monitored with a seismic network for a comparable duration. The data has been reanalyzed dozens of times with increasingly sophisticated techniques, and each reanalysis has yielded new insights. Webber's 2011 study of the lunar core used the same raw data collected in the 1970s, applied modern computational methods, and discovered the layered core structure that had been hidden in the noise of the original recordings. But there is only so much that can be extracted from a 50-year-old dataset, recorded by 4 instruments in one small region. To move the science forward, new seismic data is needed. New seismometers on the moon, more of them, in different locations, with modern sensitivity and modern digitization. And that is exactly what the next decade promises to deliver. The Farside Seismic Suite, a NASA-supported payload, is scheduled to be delivered to Schrödinger Basin on the far side of the moon by a commercial lander as part of NASA's Commercial Lunar Payload Services initiative. It will carry 2 seismometers designed to operate in the extreme conditions of the lunar far side, where temperatures swing between scorching heat and extreme cold on a 2-week cycle. Schrödinger Basin is a large, relatively young impact structure, and its location on the far side means that any seismic data it collects will fill a gap that has existed since the Apollo era. No seismometer has ever operated on the far side of the moon. We have never listened to what is happening beneath half of the lunar surface. The Lunar Environment Monitoring Station, co-led by Nicholas Schmer of the University of Maryland, is being developed as a potential payload for the Artemis 3 mission to the South Polar region. If deployed, it would provide the first seismic monitoring of the lunar South Pole, the very region where the strongest shallow moonquake was recorded by Apollo, and where the densest concentration of young thrust faults has been identified. The instrument would assess the seismic hazard in real time, providing data that would be directly relevant to the safety of the astronauts on the surface and to the planning of any future permanent installations in the area. China's Chang'e 7 mission, beyond its primary focus on water ice, will also carry instruments capable of contributing to the seismic picture, and a growing number of private and international missions planned for the mid to late 2020s we'll add seismometers, gravimeters, and heat flow probes to the mix. Within a decade, the Moon could go from being one of the least seismically monitored worlds in the inner solar system to one of the most monitored. The data that comes back will not just refine our understanding of the Moon, it will test our models of how all rocky worlds evolve, cool, contract, and eventually go quiet. The Moon is a laboratory, and we are about to open it. There is another dimension of the Moon's strangeness that weaves through everything we have discussed, but deserves to be addressed directly. The Moon is not symmetrical. The side that faces us and the side that faces away are fundamentally different worlds, and nobody is entirely sure why. The near side, the face you see when you look up at night, is dominated by the dark Maria, the vast basaltic plains that were created when ancient lava flows filled the Great Impact Basins. These plains cover roughly 31% of the near side's surface. They are flat, relatively smooth, and composed of dense iron-rich basalt that erupted from the interior between 3.8 and 2 billion years ago. The far side, which was first seen by human eyes when the Soviet Luna 3 spacecraft photographed it in 1959, looks nothing like the near side. It is almost entirely covered in bright island terrain. The Maria that dominate the near side are nearly absent on the far side. Instead, the landscape is a dense, chaotic jumble of craters of all sizes, piled on top of each other in a record of bombardment that stretches back to the earliest days of the solar system. The far side's crust is significantly thicker than the near side's, roughly 60 miles compared to 40, and it contains a much lower concentration of the radioactive elements, uranium, thorium, and potassium, that generate internal heat through decay. This dichotomy is one of the Moon's most profound mysteries. Why should one hemisphere be so different from the other? The impact basins on the near side are not significantly larger or more numerous than those on the far side. The difference is in what happened after the impacts. On the near side, the basins were flooded with lava. On the far side, they were not. The near side's crust was thin enough and hot enough to allow magma from the interior to reach the surface. The far side's thicker crust acted as a lid, preventing the lava from erupting even where large impacts had created basins that could have served as receptacles. Several hypotheses have been proposed to explain the asymmetry. One suggests that the distribution of radioactive elements is uneven, with a concentration on the near side that produced more internal heat and thinner crust in that hemisphere. This concentration, known as the Procellarum creep terrain, named for potassium, rare earth elements, and phosphorus, is centered on the near side and is associated with the most volcanically active region of the Moon's history. Another hypothesis invokes the tidal interaction with Earth. When the Moon was young and close, Earth's tidal forces may have been strong enough to preferentially heat the near side, thinning the crust and promoting volcanism on the hemisphere facing the planet. A third hypothesis, more dramatic, proposes that a massive impact on the far side, early in the Moon's history, perhaps the event that created the enormous South Pole Aitken Basin, one of the largest impact structures in the solar system, redistributed crustal material in a way that permanently altered the thickness of the crust on both hemispheres. The truth may involve elements of all three. What matters for our purposes is that the Moon's interior is not uniform. The processes driving the contraction, the faulting, the seismic activity, and the potential outgassing do not operate identically on the near side and the far side. The thicker far side crust may respond differently to compressive stress than the thinner near side crust. The distribution of heat-producing elements affects the local rate of cooling and therefore the local rate of contraction. And the deep moonquake sources identified by Apollo are concentrated on the near side, though this may be an observational artifact of the seismometer network being located exclusively on the near side. This is why the far side seismic suite matters so much. Until a seismometer operates on the far side, we cannot know whether the far side is seismically similar to the near side or fundamentally different. We cannot know whether the deep moonquake sources are truly concentrated on one hemisphere or distributed globally. We cannot know how seismic energy propagates through the thicker far-side crust compared to the thinner near-side crust, and we cannot know whether the ongoing contraction is producing the same density of faults and ridges on both hemispheres, because the orbital imaging that identified the near-side features has lower resolution and less coverage on the far side. The Moon's asymmetry is not a footnote. It is a central feature of its geology, and any complete understanding of the Moon's evolution must account for it. The fact that we are still debating its cause, more than 60 years after we first photographed the far side, is a reminder of how much remains unknown about a world that sits just 3 days' travel from Earth. But even before those instruments are deployed, the data we already have tells a story that is worth sitting with, because the Moon's ongoing transformation is not just a scientific curiosity. It has practical implications for the missions we are planning right now, for the structures we intend to build, and for the assumptions we have been making about the safety of the place where humanity is about to return for the first time in half a century. NASA's Artemis 3 mission is designed to land astronauts at the lunar South Pole. This is not a return to the equatorial plains where Apollo touched down. The South Pole is a fundamentally different environment. The terrain is rugged. Craters with walls rising thousands of feet above their floors dominate the landscape. Permanent shadows fill the deepest depressions, creating pockets of darkness where the sun has not shone in billions of years. And it is exactly this terrain, with its steep slopes, its shadows, and its extreme temperature gradients, where the Moon's ongoing tectonic activity poses the greatest risk. The 2024 study by Waters, Schmer, and colleagues was explicit about this. Among the 9 refined candidate landing regions announced by NASA in October of that year, one in particular drew attention. the Gerlachia Rim, 2, a site on the rim of a large polar crater, sits in uncomfortable proximity to a young thrust fault scarp. The modelling performed by the research team showed that the formation of this scarp was consistent with a moonquake of the magnitude recorded by the Apollo seismometers in the 1970s, and the same team showed that steep slopes in the surrounding area are susceptible to regolith landslides triggered by even light seismic shaking. The word light is important here. On Earth, a magnitude 3 earthquake is barely noticeable. You might feel a gentle tremor and think nothing of it. On the Moon, a magnitude 3 event could persist for 10 minutes or more, and on a slope covered in loose dry powder with no cohesion and no moisture to hold it together, even a gentle but prolonged shaking could set material in motion. The permanently shadowed regions that contain the most scientifically valuable ice deposits are often located on or near these steep interior crater walls. A landslide triggered by a distant shallow moonquake could bury instruments, alter the distribution of surface ice, or create a dust cloud that takes hours to settle in the Moon's weak gravity. Thomas Waters has been careful to note that for a short-duration mission like Artemis 3, the probability of a strong shallow moonquake occurring during the few days astronauts are on the surface is extremely low. The 28 shallow quakes recorded over 8 years of Apollo monitoring translate to an average of roughly 3 or 4 per year, and they were distributed across the entire Moon. The chance that one occurs at the South Pole during any given week is vanishingly small. But Artemis 3 is not the end of the plan. It is the beginning. The Artemis program is designed to establish a sustained human presence on the Moon. NASA has discussed plans for a lunar gateway, a small space station in lunar orbit. There are proposals for semi-permanent surface habitats. International partners and private companies are developing plans for mining operations, research stations and infrastructure that would remain on the lunar surface for years or decades. On those timescales, the seismic risk changes character entirely. A probability that is negligible over a few days becomes significant over a few years and serious over a few decades. A permanent base at the South Pole would need to be designed not just to survive a moonquake, but to survive repeated moonquakes over its operational lifetime, each one producing sustained shaking that lasts far longer than any terrestrial earthquake. The engineering is not impossible. We build structures on Earth that withstand repeated earthquakes in seismically active zones, but the lunar environment introduces complications that do not exist on Earth. There is no soil moisture to provide cohesion. The regolith is an extraordinarily fine abrasive powder that has been ground to dust by billions of years of meteorite impacts. It is electrostatically charged and clings to everything. A structure shaken for 20 minutes in this material would experience mechanical stresses and surface abrasion that have no terrestrial analogue. And there is the ringing bell problem. On Earth, a building designed for earthquake resistance needs to withstand perhaps 60 seconds of strong shaking, followed by rapidly diminishing aftershocks. On the Moon, the same energy level persists for 10 to 20 times longer. The resonant frequencies of a structure interacting with sustained lunar seismic waves might produce amplification effects that would not occur during a brief terrestrial earthquake. The engineering has not been done in detail because the seismic data from the South Pole does not yet exist. That is precisely what the Lunar Environment Monitoring Station is designed to provide. There is another dimension to the seismic hazard that has received less attention in public discussions. The Apollo Seismic Network recorded 4 types of moonquakes, and the shallow ones are the most dangerous. But the deep moonquakes, the tidally driven events originating hundreds of miles below the surface, also have implications for long-term surface operations. They are individually weak, typically below magnitude 2, but they are numerous and they occur in clusters. The Apollo network identified at least 318 separate deep moonquake sources, each one a specific location in the deep interior that produces quakes repeatedly as the moon orbits Earth and experiences tidal flexing. Some of these deep moonquake sources produced events every 27 days, synchronized with the moon's orbital period. Others fired more irregularly. The cumulative effect of hundreds of small, regularly recurring seismic events on a structure or a mining operation over years is a question that fatigue engineers and structural analysts will need to address. It is not a showstopper, but it is a design constraint that does not apply to any structure on Earth and has never been tested in the lunar environment. The thermal moonquakes add yet another layer of complexity. Every 2 weeks the lunar surface transitions between scorching sunlight and frigid darkness. The thermal shock at the terminator, the boundary between the lit and unlit portions of the surface, generates seismic signals as the surface rock expands and contracts. At the South Pole, where the sun is always near the horizon and the terminator sweeps across the terrain at a low angle, the thermal environment is particularly dynamic. Areas of permanent shadow sit immediately adjacent to areas of near-permanent sunlight. The thermal gradients are extreme over short distances, and the seismic signature of those gradients has never been measured. All of these hazards are manageable individually. NASA has decades of experience building structures and equipment that operate in extreme environments. But the combination of sustained moonquakes, thermal cycling, regolith instability, radiation exposure, and the logistical challenges of operating 238,000 miles from the nearest hospital creates a risk environment that demands more data than we currently have. That data is coming, but it is not here yet, and the decisions about where to build, how to build, and what to expect are being made now with the data we have, which is largely data from 50-year-old instruments deployed in a different region of the moon. Beyond the immediate engineering questions, the moon's ongoing evolution raises scientific questions that are still unanswered. The most fundamental of these is a question about the rate of change. Is the moon's contraction constant, or does it vary over time? The scarps and ridges mapped by the Lunar Reconnaissance Orbiter camera are young, but how young? Were they formed 1 million years ago? 100 million? Were they formed in a steady trickle, one here and one there, spread evenly across time? Or did they form in clusters, with periods of more intense activity, separated by periods of relative quiet? The answer matters, because it affects the seismic hazard assessment. If the faulting is steady and evenly distributed in time, the probability calculations are straightforward. If the faulting comes in bursts, there could be periods of elevated risk separated by periods of calm, and we would need to know where in that cycle the moon currently stands. There are hints in the data. The deep moon quakes recorded by Apollo showed a strong tidal periodicity, which suggests that at least some of the moon's seismic activity is modulated by its orbital dynamics. The shallow moonquakes did not show such clear periodicity, but the sample size was small, only 28 events over 8 years, which is not enough to establish a pattern with confidence. Similarly, the magnetic field history shows what appears to be episodic behaviour. If the February 2026 Nature geoscience study is correct, and the lunar dynamo flickered on and off in response to episodic magma upwellings, that suggests the moon's internal processes can be intermittent rather than continuous. Whether that same intermittency applies to the current tectonic regime is unknown. The geological record of the moon itself, preserved in the ancient surface, offers some clues. The Labat scarps and small mare ridges mapped by orbital cameras have been dated roughly by their superposition relationships, which scarps cut across which craters and which ones are buried by more recent features. This kind of relative dating can establish a sequence but not a precise timeline. Some researchers have attempted to estimate the ages of the scarps by examining the degradation state of the craters they cross, using models of how quickly small craters are eroded by micrometeorite bombardment on the moon. These estimates suggest that many of the scarps are less than a few 100 million years old, and some may be significantly younger. If the scarps are indeed that young, and if the rate of scarp formation is roughly constant, the moon is producing new faults on a timescale that is geologically rapid. New cracks in the crust, new potential moonquake sources appearing every few million years. On human timescales, that is undetectable. On the timescales relevant to a permanent base, it means the hazard map is not static. It evolves slowly as the moon continues to cool and contract. There is also the question of the moon's internal heat budget. How much residual heat remains in the interior, and at what rate is it being lost? The Apollo missions deployed heat flow probes at 2 sites, Apollo 15 and Apollo 17, and measured the rate at which heat was escaping from the interior through the surface. The values they obtained, approximately 21 milliwatts per square meter at the Apollo 15 site and 16 milliwatts per square meter at the Apollo 17 site, were higher than some models had predicted. But 2 measurements at 2 equatorial sites do not characterize a global heat flow. The heat loss rate may vary significantly with latitude, crustal thickness and local geology. The far side, with its thicker crust, may be losing heat at a different rate than the near side. The polar regions, where the surface is never fully heated by the sun, may have a different thermal profile entirely. Without a network of heat flow measurements distributed across the moon, the global thermal budget remains uncertain, and with it, the rate and future trajectory of the contraction. These are not abstract questions. They bear directly on the most basic planning decisions for lunar infrastructure. Where is it safe to build? How strong do the foundations need to be? What is the expected seismic loading over a 30-year operational lifetime? What maintenance will the structures require? How frequently will systems need to be inspected for damage from thermal cycling and seismic fatigue? None of these questions can be fully answered with the data we have today. All of them will begin to be answered in the next decade, as new instruments reach the surface and new missions return samples from locations that the Apollo program never visited. The moon has been studied more intensively than any object in space other than Earth. Yet the gaps in our knowledge remain enormous. We have seismic data from 4 stations on one hemisphere, collected over 8 years with 1970s era instruments. We have heat flow measurements from 2 sites. We have rock samples from 9 locations, all near the equator or in the mid-latitudes, with the single exception of the Chang'e 5 sample from a relatively young volcanic plain. We have orbital data that is excellent for surface mapping, but cannot tell us what is happening deep inside. The moon is close. It it is accessible, and the questions it poses are answerable with technology that already exists. What the next generation of lunar science needs is not a breakthrough in theory. It needs instruments on the surface, more seismometers, more heat flow probes, more sample return missions, especially from the polar regions and the far side, where the geological history is most different from the near-side equatorial sites that Apollo sampled. The Artemis program, for all its technical and political complexity, has the potential to transform our understanding of the Moon more profoundly than any mission since Apollo. Not because it will send astronauts, though that is symbolically and practically important, but because it will deploy instruments in a region of the Moon that has never been measured directly. The South Pole is not just a destination for human exploration. It is the location where the Moon's active tectonic processes are most clearly expressed, where the ice deposits are most accessible, and where the geological history is most directly relevant to the safety and feasibility of sustained operations. Everything we have discussed tonight, the quakes, the shrinkage, the drift, the water, the dead field and the flashes, converges at the South Pole. It is the place where the Moon story is most active, most relevant, and most in need of direct observation. And we are about to go there. Not just one nation, not just one agency. The Moon is entering a period of exploration more intense than anything since the Apollo era, and arguably more sustained. NASA's Artemis program aims to land astronauts at the South Pole and establish the infrastructure for repeated visits. China's lunar program, already the most successful robotic exploration campaign since the Soviet Union's, is preparing Chang'e 7 for a South Polar mission, with water ice detection as its primary goal, and has announced plans for a permanent international lunar research station to be built in the 2030s. India's ISRO, building on the success of Chandrayaan-3's South Polar landing, is planning Chandrayaan-4, a sample return mission. Japan's Slim Lander demonstrated precision landing technology in early 2024. The European Space Agency is contributing instruments and hardware to multiple international missions, and a growing fleet of commercial landers, developed by companies like Intuitive Machines and Astrobotic, under NASA's Commercial Lunar Payload Services program, are providing a pipeline of delivery opportunities that did not exist a decade ago. The convergence of these programs on the lunar South Pole is not a coincidence. It is driven by the science we have been discussing all night. The South Pole is where the ice is. The South Pole is where the active faulting is most clearly documented. The South Pole is where the permanently shadowed craters preserve billions of years of volatile accumulation. And the South Pole is where the strongest recorded shallow moonquake originated, near the exact location where multiple nations are now planning to send their most ambitious missions. The competition and collaboration playing out in lunar space right now will produce more data about the Moon in the next 10 years than the previous 50 combined. Every lander carries instruments. Every orbiter photographs the surface at higher resolution. Every sample returned to Earth adds to the library of lunar materials that scientists can analyze with laboratory techniques far more sensitive than anything available in the 1970s. The understanding of the Moon that it exists in 2035 will be as different from today's understanding as today's is from the understanding that existed before Apollo, and every piece of that new understanding will feed back into the questions we have been exploring tonight. How fast is the Moon contracting? Where are the faults, and how often do they slip? How much ice is there, and where exactly is it? What is the interior structure of the far side? Is the contraction accelerating, decelerating, or steady? When did the dynamo truly die, and what powered its final stages? Are the transient flashes connected to the tectonic activity? And if so, can they be used as indicators of ongoing geological processes? These are answerable questions. The instruments exist. The missions are funded. The launch dates are on the calendar. What has been the loneliest scientific frontier in planetary science? a single world monitored by 4 instruments in one hemisphere for 8 years and then left silent for nearly half a century, is about to become one of the most intensively studied surfaces in the solar system. But before we bring this to a close, there is one more thing to sit with. Something broader than any single measurement or mission plan. Something about what the moon's slow transformation tells us about the nature of the worlds around us and the scale of time on which they operate. The moon was born in violence. The leading theory of its origin, the giant impact hypothesis, describes an event so catastrophic that it is difficult to fully comprehend. Approximately 4.5 billion years ago, the young Earth, still partially molten, still accumulating the last of the debris that would form its final mass, was struck by another planetary body roughly the size of Mars. This object, which scientists have named Theia, collided with Earth at an angle, and the impact released so much energy that it vaporized significant portions of both bodies. The debris from the collision formed a ring of superheated rock and metal orbiting the shattered Earth. Over a period of perhaps a few hundred years, this ring coalesced under its own gravity into the moon. The newborn moon was close, perhaps as close as 15,000 miles from Earth's surface, compared to 238,900 miles today. At that distance, it would have dominated the sky, appearing more than 15 times larger than it does now. The tidal forces between the two bodies at that proximity were immense. Earth's day lasted only a few hours. The moon orbited rapidly, and the gravitational interaction between the two bodies was so intense that it generated tides not just in the oceans, which may not have fully formed yet, but in the rock itself. The surface of the young Earth flexed and buckled under the moon's gravitational pull. The moon was hot, not just warm. The impact that created it had deposited enough energy to melt the entire body. The moon began its existence as a ball of liquid rock, a magma ocean hundreds of miles deep, glowing red hot in the sky above a similarly devastated Earth. Over the next several 100 million years, that magma ocean cooled and solidified, forming the anorthosite crust that still constitutes the bright highlands, visible from Earth today. The heavier minerals sank toward the centre, forming the mantle and the iron core. The lighter minerals, rich in calcium and aluminum, floated upward and crystallized into the light-coloured surface rock. As the interior solidified, the core remained liquid for a time, churning with convective currents driven by the residual heat of formation and by the tidal flexing from nearby Earth. That churning generated the magnetic field that we discussed earlier, a field strong enough to shield the young moon's surface from the worst of the solar wind. Then the bombardment came. Between approximately 4.1 and 3.8 billion years ago, a period known as the Late Heavy Bombardment. The inner solar system was pummeled by a rain of asteroids and comets, remnants of the planetary formation process that had been gravitationally disturbed into new orbits. The moon, lacking an atmosphere to protect it, absorbed the full force of this bombardment. The great basins visible on the near side, Imbrium, Serenitatis, Chrysium, Nectarium and many others, were excavated during this period, enormous craters hundreds of miles across that were later filled with basaltic lava erupting from the interior. The volcanism was the last great expression of the moon's internal energy. From roughly 3.8 billion years ago to perhaps 1 billion years ago, lava periodically flooded the Great Basins, creating the Dark Maria, the flat expanses of basalt that form the features we see as the face of the man in the moon. Each eruption was less voluminous than the last. Each lava flow was thinner. The intervals between eruptions grew longer. The moon was cooling, and its ability to generate and deliver magma to the surface was fading. The youngest basalts returned by the Chang'e, 5 mission in December 2020, are approximately 2 billion years old. They represent some of the last volcanic products the moon ever created. Since then, the interior has continued to cool. The core has largely or entirely solidified. The magnetic field has collapsed, and the only geological activity remaining is the slow contraction and faulting that we have been tracing throughout this conversation. Imagine compressing that entire history into a single day. At midnight, the giant impact occurs. By 1 in the morning, the moon has a magma ocean and is beginning to solidify. By 3 a.m., the crust has formed and the magnetic field is active. Between 3 and 4 a.m., the late heavy bombardment reshapes the surface. From 4 a.m. through about noon, volcanic eruptions periodically flood the basins. The magnetic field dies around 2 in the afternoon. The last lavas erupt around 5 p.m. And from 5 p.m. to midnight, an expanse of 7 hours, the moon does essentially one thing. It cools, it contracts, it cracks, and it drifts slowly away from Earth. We are currently at about 11:58 p.m. in this compressed timeline. The moon has been in its current quiet phase for the vast majority of its history as measured by activity, but only a fraction of its history as measured by time. The fireworks happened early and fast. The silence has lasted far longer. What remains of those fireworks is written everywhere on the surface. The craters preserve the bombardment. The Maria preserved the volcanism. The magnetic anomalies preserve the field. The regolith, the powdery soil covering the surface to a depth of several meters, preserves billions of years of meteorite impacts, solar wind exposure, and cosmic ray bombardment. Every grain of lunar soil is a record. Every rock returned by Apollo or Chang'e is an archive. And here is something remarkable about those archives. Because the moon has no atmosphere, no water, no tectonic recycling, and no biological activity, the records it preserves are far more pristine than anything that survives on Earth. Earth's surface is constantly being remade. Plate tectonics recycles the crust. Water erodes and deposits. Life transforms the chemistry of the surface and the atmosphere. The oldest rocks on Earth are approximately 4 billion years old, and they have been altered by metamorphism, folding, and chemical weathering. On the moon, rocks that crystallized 4.4 billion years ago sit essentially undisturbed on the surface, their mineral grains still aligned to the magnetic field that existed when they cooled, their chemical composition unchanged, their isotopic ratios frozen in time. This makes the moon not just a scientific target but a time machine. The geological history of the inner solar system is better preserved on the moon than anywhere else within reach. Events that have been erased from Earth's record by billions of years of geological activity, the conditions of the early solar system, the intensity of the early bombardment, the composition of the early solar wind, even traces of Earth's own ancient atmosphere potentially transferred to the moon by the solar wind when the two bodies were closer. All of these may be accessible in the Lunar Geological Record. The 2024 study by Taduno and colleagues, the one that challenged the long-lived dynamo hypothesis, made this point explicitly. If the moon lacked a magnetic field for most of its history, then its surface has been directly exposed to the solar wind for over 4 billion years. During that time, some of the particles carried by the wind originated from Earth's own upper atmosphere, swept up by the geomagnetic field and funneled outward into space. When the moon was closer to Earth, the probability of these terrestrial particles reaching the lunar surface was higher. It is possible, the researchers suggested, that components of Earth's ancient atmosphere, its Archean or even Hadean atmosphere, are trapped in the buried lunar regolith, preserved in a form that no longer exists anywhere on Earth. If that is true, then the moon contains not just its own history, but a piece of Earth's, the air that the first living organisms breathed, or the air that existed before life began, might be recoverable from samples of ancient lunar soil buried beneath the surface. This is speculative, but it is physically grounded, and it is one of the most compelling scientific motivations for a sample return mission to a location on the moon where ancient, deeply buried regolith can be accessed. The moon is a witness. It has been sitting 238,000 miles away, watching for the entire history of life on Earth. Every asteroid that struck this part of the solar system, every fluctuation in the sun's output, every change in the composition of the solar wind has left its mark on the lunar surface, and unlike Earth, which erases its marks like a palimpsest, the moon keeps them. This is what makes the moon's ongoing transformation so scientifically poignant. It is not just that the moon is still active, it is that it is still active in the same way it has been active for billions of years, through the single mechanism of interior cooling, and we have the opportunity to study that mechanism in real time. Every new fault scarp that forms, every moonquake that shakes the South Polar regolith, every burst of radon that escapes through a fresh crack, is a continuation of a process that has been operating since the magma ocean first began to solidify. We cannot watch Earth's core dynamo in real time. The core is 1,800 miles down and surrounded by thousands of miles of rock and metal. We infer its behaviour from surface magnetic measurements and from the seismic waves that pass through it. But the moon is smaller. Its processes are more accessible. Its surface directly reflects its internal state, in ways that Earth's surface does not, because the moon lacks the buffering layers of atmosphere, ocean and biosphere that insulate Earth's surface from its interior. Studying the moon's ongoing evolution is, in a very real sense, studying how all rocky worlds age and die. The moon is a small world at the end of its geological life. Mars is a medium-sized world, somewhat further along than Earth but not as far gone as the moon. Earth is a large world still in its geological prime. Mercury is a small world with a massive core that tells a different version of the same story. By comparing these bodies, their cooling rates, their magnetic histories, their tectonic expressions, and their atmospheric evolution, scientists can build a general theory of planetary life cycle that applies not just to our solar system, but to the rocky worlds orbiting other stars. The discovery in the last 2 decades that the moon is more active than anyone expected, that it is still shrinking, still quaking, still producing tectonic features, still possibly outgassing, has enriched this comparison immensely. A world that was thought to have nothing left to teach us about active geology turned out to be a laboratory for studying the very end stages of that process, the final tremors and adjustments of a world in the last chapter of its geological story. And there is a deep, almost philosophical dimension to all of this that is worth acknowledging as we approach the end of tonight's exploration. The moon looks the same to you as it looked to your great-great-grandparents. It will look the same to your great-great-grandchildren. On any human timescale, the changes we have discussed are invisible. The 150-foot shrinkage distributed over hundreds of millions of years, the 3.8 centimeters of annual recession, accumulated over a human lifetime into roughly 3 meters, about the height of a basketball hoop, utterly undetectable to the eye. The quakes that last for hours but occur only a few times a year across the entire surface. These are changes that only instruments can detect. They are real, they are ongoing, and they are consequential for our plans to return, but they operate on timescales that are fundamentally different from the ones that govern a human experience. The moon is changing on a schedule that has nothing to do with us. It was changing long before there were eyes to see it, and it will continue changing long after every structure we build on its surface has crumbled to dust. That perspective is part of what makes lunar science so compelling and so humbling. We are studying processes that began before life existed on Earth and will continue after the sun has exhausted its fuel. The moon's contraction will not stop until its interior reaches thermal equilibrium with the vacuum of space, a process that will take billions of years more. The recession from Earth will continue until the sun's expansion engulfs both bodies. The craters will accumulate, one meteorite at a time, resurfacing the terrain on timescales of hundreds of millions of years. The moon is patient in a way that nothing in human experience is patient, and the instruments we send to study it need to be patient too, running for years, decades, accumulating data point by point, building a picture of processes that unfold too slowly for any single mission to fully capture. There is something else that the moon's ongoing evolution brings into sharp focus, something that the reference point of Earth's own geological activity makes particularly clear. The moon and Earth are connected. They have been connected since the moment of the moon's creation, bound by gravity, exchanging angular momentum through tidal forces, influencing each other's rotation, each other's geology, each other's evolution. The moon's recession from Earth is not just a lunar phenomenon, it is an Earth phenomenon. The energy that pushes the moon outward comes from the Earth's rotation. Our days grow longer because the moon's orbit grows wider. The tides that shape our coastlines are the same tides that stress the moon's crust and trigger deep moonquakes. Every shallow moonquake that cracks the lunar surface releases energy that was stored by the slow cooling of an interior that has been losing heat since the giant impact 4.5 billion years ago. But the deep moonquakes, the most common type recorded by Apollo, are tidally driven. They are caused by Earth. Every 2 weeks, as the moon follows its elliptical orbit and passes through perigee, the point of closest approach, Earth's gravity squeezes the lunar interior slightly harder, and the deep rocks flex. The strain accumulates along specific fault zones deep in the mantle, and when the strain exceeds the strength of the rock, the fault slips and a deep moonquake occurs. There are more than 160 identified deep moonquake source zones, each one a specific location in the moon's deep interior that produces quakes repeatedly in response to tidal forcing. Some of these zones have been active throughout the entire 8-year Apollo monitoring period, and presumably for far longer. They are scars in the moon's deep structure, places where the rock is weakest, where Earth's gravitational flexing concentrates stress, and where the accumulated strain periodically releases in a small seismic event. This means that Earth is, in a literal physical sense, shaking the moon every orbit, every month, continuously, for billions of years. The connection between the two bodies is not just gravitational, it is mechanical. Earth's gravity reaches into the moon's interior and manipulates its structure, generating the most common type of seismic activity on the lunar surface, and the moon returns the favour. The tidal forces the moon exerts on Earth do not just move the oceans. They flex the solid Earth, they slow the rotation, and they influence the distribution of stress in Earth's tectonic plates. The relationship between the Earth and the moon is the longest, most intimate gravitational partnership in the inner solar system. It has shaped both bodies for their entire histories. It will continue to shape them until the sun ends the conversation. Let us take a moment now to simply sit with what we have covered tonight, because the full picture, assembled from all these pieces, is something worth contemplating as a whole. The moon was born from a collision of worlds. It began as a sphere of molten rock, glowing in the sky above a shattered Earth. Over hundreds of millions of years, it cooled and solidified, forming a crust of light-coloured anorthosite, a mantle of dense silicate, and a core of liquid iron. The core churned and generated a magnetic field that may have rivaled Earth's. Volcanoes erupted lava across the surface, filling the great impact basins with dark basalt. The bombardment of asteroids and comets tapered off, leaving the cratered landscape we see today. Then the long decline began. The interior kept cooling. The core began to solidify. The magnetic field weakened, flickered, and eventually died. The volcanism slowed, each eruption smaller and less frequent than the last, until the last lava flow spread across the surface roughly 2 billion years ago, and no more followed. The moon entered its current phase, the long twilight of a world whose engine is running down, but not yet fully stopped. In that twilight, the contraction continues. The crust cracks and faults. The quakes propagate through the rigid interior and ring for minutes or hours. Gas escapes through new fractures and briefly glows in the vacuum. Ice accumulates in the permanent shadows of polar craters, molecule by molecule, delivered by comets and the solar wind and preserved by the absence of everything that would destroy it on a more active world. And the whole body drifts slowly outward, carried by the tidal exchange of angular momentum with the planet that created it. This is what is happening on the moon right now. Not the dramatic geology of its youth, not the cataclysmic impacts of the bombardment era, not the rivers of lava that created the Maria. What is happening now is quieter, slower, subtler, but it is real. and it is measurable, and the instruments we have built to detect it are among the most precise that humanity has ever created. The Apollo seismometers, deployed by astronauts who walked on the surface and drove a rover across its plains, recorded the moon's trembling for 8 years before they were switched off. The Lunar Laser Ranging Experiment, consisting of simple mirrors placed on the surface, has been tracking the moon's recession for more than 50 years with centimetre accuracy. The Lunar Reconnaissance Orbiter camera, orbiting just 31 miles above the surface, has photographed the fault scarps and ridges with resolution fine enough to identify individual boulders. Chandrayaan-1's instruments detected water that had been invisible to every previous observer. Elkiros confirmed ice by crashing a rocket into a dark crater and reading the resulting plume. And Chandrayaan-3's thermometer, pressed into the soil of the South Polar region, measured temperature variations that point toward ice deposits in places nobody had thought to look. Each instrument answered a question, and each answer opened new questions. That is how science works, not in dramatic revelations, but in a slow tightening of the picture, a gradual convergence toward understanding that is never complete, but always improving. The next decade will bring more instruments, more answers, and more questions. The Far Side Seismic Suite will listen to a part of the moon that has never been monitored. The Lunar Environment Monitoring Station will measure the seismic risk at the South Pole in real time. Chang'e 7 will search for ice in the permanent shadows of Shackleton Crater. Artemis will deploy astronauts at the South Pole for the first time in human history, and those astronauts will collect samples, deploy experiments, and begin the process of turning the moon from a destination into a workplace. When they arrive, they will stand on a world that is shrinking beneath their feet at a rate too slow to feel. The ground they walk on will be the same dry, powdery regolith that Apollo astronauts described as like walking on talcum powder, but it will be a surface that we now know is undergoing active tectonic deformation. Somewhere beneath them, hundreds of miles down, the remnants of a once liquid core sit in near or complete solidity, the same core that once generated a magnetic field strong enough to deflect the solar wind. That field is gone. The radiation environment they will face is the unfiltered output of the sun, mitigated only by the shielding of their suits and their habitat. In the craters nearby, in the permanent shadows where temperatures drop below minus 230 degrees Celsius, there is ice. We know it is there. We have detected it from orbit, confirmed it through impact experiments, and modelled its distribution using surface temperature data. The ice is both the reason for going and the key to staying. If it can be extracted and processed, it provides water, oxygen, and fuel. If it cannot, if the deposits are too thin, too dispersed, or too deep to be practically mined, the economics of sustained lunar operations change dramatically, and around the astronauts, on slopes they can see but cannot safely climb, the evidence of the moon's ongoing contraction will be visible, scarps where one section of the crust has been thrust up over another, ridges where compressive forces have buckled the surface into low mounds, fresh-looking fractures cutting across older terrain, all of it, the surface expression of a world that is still, after 4.5 billion years, adjusting to the loss of its internal heat. This is the moon we are returning to, not the dead, simple finished world that the pre-Apollo era imagined, not the inert proving ground that the original space race treated it as, a world that is geologically active, hydrologically interesting, seismically hazardous, and scientifically invaluable, a world that has more to tell us about the history of the solar system than any other body within reach, a world that is still, in its quiet, patient way, in the process of becoming whatever it will be next. There is comfort in that patience. The moon has survived 4.5 billion years of impacts, volcanic eruptions, magnetic collapse, and solar bombardment. It has absorbed every blow and continued its slow, steady evolution without interruption. The changes we have discussed tonight are not crises, they are processes. They unfold across millions and billions of years, and they produce consequences that are measurable but not catastrophic, significant for engineering but not for survival, important for science but not alarming for daily life. The moon you will see tonight, if the sky is clear, looks exactly as it did the night you were born. The same craters, the same Maria, the same pale light reflected from the same ancient surface. Nothing visible has changed, and nothing visible will change in your lifetime or in the lifetimes of many generations to come. But beneath that unchanging face, the interior is still releasing its heat. The crust is still adjusting to the contraction. The faults are still capable of slipping and producing quakes that ring through the body for minutes or hours. The ice in the shadows is still accumulating, molecule by molecule, and the whole world is still drifting away from us, centimetre by centimetre, year by year, carrying with it the geological record of the solar system's earliest days and the faint preserved traces of an Earth that no longer exists. Something strange is happening on the moon. It has been happening for billions of years. It is getting neither better nor worse. It is simply continuing, the way all things in the universe continue, on timescales that dwarf our comprehension, and with a steadiness that puts human impatience to shame. The instruments are watching. The data is accumulating. The scientists are reading it, arguing about it, refining their models and preparing to go back for more. In the next few years, for the first time since 1972, human beings will stand on the lunar surface and look at Earth rising above the horizon. They will be standing on a world that we now know is far more interesting, far more active, and far more connected to our own planet than anyone understood when the last astronauts left. They will also be standing on a world that is extraordinarily quiet. No wind, no weather, no sound of any kind, just the faint vibrations of a body still cooling from its formation, still adjusting to the slow loss of its internal warmth, still doing the work that all rocky worlds do in the fullness of time. Everything we have discussed tonight is confirmed science. The measurements are real. The instruments are calibrated. The data has been reviewed, challenged, replicated and published. The moon is shrinking. It is quaking, it is drifting. It contains water. Its magnetic field is dead. Its surface produces unexplained flashes. And all of these phenomena are connected through the single thread of thermal evolution, the slow bleeding of heat from the interior of a world that was born in fire and is gradually cooling to equilibrium with the vacuum of space. That process will take billions of years more to complete. The moon will still be contracting, still faulting, still quaking, long after every human structure on its surface has been buried under the regolith and forgotten. It will still be drifting away from Earth when the sun begins to expand, and the ice in its shadowed craters will still be there, molecule by molecule.